So, first of all, I have to apologize. The version of the slides you're going to see is not the latest version. And here's an advice to all you hackers. If you're drunk and stoned and you think it's a good idea to clean up your conference laptop before you go to the conference, don't. Especially because you might happen to delete the directory that is containing the presentation for the conference you're going to, which I happen to manage to do. So this is a older version, but just slightly older. That's about me. So what are we covering? So everyone is familiar with Stuxnet in general, but I would like to actually give you a little bit more details about it, so you can appreciate the engineering done with this piece of targeted malware. If you're in software development or your company is in software development, please make note, this is how you build actual good software. So if all our production software like SAP or whatever, Outlook would be engineered the same way Stuxnet was engineered, we wouldn't have a lot of problems that we have today. So, and this is actually a showcase in good engineering. So let's start off with what are the actual goals of attacking industrial control processes? So there is a couple of documented attacks on industrial control processes. Most of them are for demonstration purpose. So we haven't seen a single one except for delaying a uranium enrichment program, which is Stuxnet. Everything else, train systems, power grid, and etc., have been done to show that it can be done. Stuxnet is the first instance where it was actually done, and it was done a lot better than in the demonstrations before. Now, when we look at attacks on industrial control processes, what is the most likely thing we're going to see? Cyber war, turning off power in the entire Western Hemisphere? No, very unlikely. What is more likely is that we're going to see harming the competition. Think about today's production cycles, let's say in the car industry. They have essentially zero storage, right? Everything is produced just in time and delivered just in time. So if you can make, let's say, the production line for rear view mirrors, fuck word, for a car manufacturer, if you can delay this production for, let's say, a week or half a week, the entire production of the car manufacturer goes down. So this is actually a very, very likely scenario, especially given the fact that pretty much every secret service in a developed world is now 50% industrial espionage and 50% military espionage. The other thing that we have seen is essentially blackmailing ICS owners. And this actually happened quite often. So in our professional life, we had a case of a manufacturer of ICS equipment, and the guy who actually wrote the code for the ICS environment just left the company and took the code with him, and essentially blackmailed the company into hiring him back as a consultant, so they could actually continue producing their products. Another case which is mentioned here is Mr. Terry Childs, who was the network administrator for the city of San Francisco, and he was kind of annoyed about the politics and he wanted to speak to the mayor. So he essentially changed all the passwords on the Cisco's and yeah, shut down the network. He managed to speak to the mayor, although that was a visit in the prison, and so this idea actually didn't pan out too well for him. And also, we have industrial espionage as an ICS attack vector. There's industries like, let's say, the chip industry. The chip industry uses the same production equipment. Everyone uses the same production equipment. There's just a few vendors that can build production equipment that can make chips from silicon, right? The only difference between one chip vendor and the other is the so-called recipes. That's essentially just a configuration file on the production line. So the configuration file makes the difference between an AMD chip and an Intel chip. So having the recipes is essentially having all the secrets of this vendor. So breaking into the ICS and just stealing the recipe without actually changing anything is a very lucrative business. When you look at industrial control processes and compare them to regular virus-infested office IT, there are some differences. The biggest difference actually is availability. In Office IT or in any other IT environment, you can actually go ahead and say, well, we have a scheduled downtime because we have to install Service Pack 350 on Exchange, right? So in ICS, let's say in Power Grids, downtime, not so good. People tend to notice. Same for wastewater cleaning. People tend to notice if you have a downtime and there's literal shit coming out of the water tap, right? So you can't actually turn shit off to fix it. The same as like antivirus, okay, that hasn't saved anyone in the last 20, 30 years, but it's actually very impossible to use. They have a lifetime of about 20 years. So if you have a bug, let's say in Siemens PLCs, then it is very unlikely that this actually gets fixed over the lifetime because you don't have downtimes. The vendors are just as dumb as we know them, but because there's no disclosure process, they're not fixing shit. You rarely have change management. Change management happens in the brains of the consultants that come on site and fix your control system. And security for them is essentially physical security. So if you make it into the production facility, that is all security you need to bypass. If you need to know how to do that, talk to Mr. Nickerson. And also even simple things like time and log correlation. So here's an example, and I can't tell you where I got this picture. This is two parts of a picture from an actual Iranian ICS. And if you look closely, you see here, there's an alarm that says, 2031, December, this is when the alarm happened. So unless someone managed to time travel, they actually don't care about the time because the real time is set here, the log-on time, which is on 2009, a lot more realistic. And you can also see that the log-on user is user 1. So also user management is not a big deal in ICS, right? Unless, of course, user 1 is an actual Iranian name. So, standard attack patterns. The actual easiest way to get into an ICS is simply by finding someone to bring the stuff in. You can, as I just mentioned, you can remove the source code from the site, or you can actually change the configuration. The second thing is, thanks to management, there is a gazillion dashboard applications. There's even an SAP subsystem that's called the SAP Plant Management, which you can configure to go into your ICS and monitor the entire production line. In a project with a customer, we once tried to configure a firewall in order to only let the ports through that SAP Plant Management would need to get the information out of the plant. Eventually, we replaced the firewall by a router, because that was equivalent to the rule set that we already had, meaning we had to open the entire thing. And those management systems are a lot easier to find, right? Because they're mostly web-based. The next thing is you can simply pre-compromise the equipment that someone needs. That is usually used by secret services when they figure out, well, this company or this country needs to build such and such production line. They're figuring out the 2 or 3 possible vendors that they could buy from. Then they get the equipment, backdoor the equipment, and sell it cheaper. The alternative way, of course, is the Chinese way or the Israeli way, where the government actually subsidizes, fuck commerce, or variant as they're called now, right? So essentially what they do is they simply subsidize half of the price from the government side. So this is the lowest bidder by far. And then, management is very predictable when they see half the price of something, they're going to buy it. Works really well. You would wonder how Huawei actually gets all their equipment into our networks. So there's other ways, of course, to get stuff that is not cheap. Miko actually found this. This is the fairly expensive Siemens control software that you need to run Siemens PLCs and to program them. And here's a user called Ahmadinejad that asks for seeding. Kind of like makes sense now. So the standard external attack pattern is actually go ahead, find some secretary pussy's workstation, compromise that one, or compromise the secretary. That is optional. From there, you compromise some servers. Best way, of course, is management systems, dashboards, but it can be just domain controllers. Then you establish a man-in-the-middle point between the operator, like the board guy with the comic sitting in front of the screen, and the actual ICS equipment. And then you modify the control system, and nobody notices. Stuxnet goes way beyond that, and we're going to cover that in a minute. So here it's not removed. I had the pleasure of actually training with a group at the Idaho National Laboratory in 2005 that were already, let's say, considering this type of attack. So the story is they made an internal video for the US government to sell their services inside the US government, which they showed me, but they said, well, I can't give you that. Turns out that in the beginning of the video, they mentioned the evil cyber terrorists and showed a Phenolit webpage, which they realized the moment they showed it to me. And so we made a deal, and they actually gave me a copy of the video. But that's the state of the art in 2005. So as you have seen, there's many of the patterns that we've seen in Stuxnet were known in 2005. It's not a big deal if you're really into something like that to actually develop the exploits. The thing is that the environment actually evolved. Like, it used to be that every control system, as Jason said in the video, every control system is different, right? You actually have to know how it works. Now, standardization is something that can actually bite your ass pretty nicely. So the military started to use commercial off-the-shelf equipment and now is wondering why they have viruses on their drone controllers. And the industrial control system people actually started to use very common technology. So the landscape really changes. There's lots of plug-and-play technology that you can put into purpose now. And so the control processes are no longer so different from each other. One example is, and that's an actual scary example, putting cables, like actual electrical cables, into a factory is very expensive because they have to be heat resistant, they have to be acid resistant, and blah, blah, blah. So you know what they're actually doing now? They're using wireless. Because Wi-Fi actually allows them to, have less cables, and it's a lot cheaper to build up the factory. So you're walking by a factory, and you have like valves on acid tanks that like scroll by a little IPv4 IP address, and like the network name and the SSID. And of course, they're not encrypted because key distribution is a problem, right? So this is actually like what the landscape is looking at right now. So now let's look at Stuxnet. Stuxnet actually comes with a range of spreading mechanisms, right? So we have the LNK vulnerability that all the AV companies jerked off about because it was a 0-day in Windows 7 and then ignored the fact that there's a lot more to Stuxnet than this. So there's the LNK, the Windows Task Scheduler, keyboard layout, print spooler, the old RPC issue. Then there's self-copying to remote network drives. There's self-copying to Siemens CNC servers and infection of Step 7 project files. That's a lot of spreading mechanisms. We also have peer-to-peer updating. So, in case you don't reach the update site, there's a CNC server There's a couple of rootkit drivers. The drivers are actually signed with code certificates. And there's circumvention of a lot of client security products, and there's a nice DLL loading routine to circumvent host-based intrusion detection systems. And so let's go into the details. Oh no, there's more. Of course, there's a fingerprinting of a ICS. There's a backdooring of the WinCC server, and this is a very nice one, is the virtualization of a PLC within itself in order to not have to do operator spoofing. So, first one, LNK. Most of you have probably looked at it. It uses a special feature. So LNK are the little files that gives you a shortcut on Windows because Windows sucks at soft links, right? So it uses a little known feature within the LNK file where usually the LNK file just says, well, this is where I'm pointing to. And then when Windows has to load the LNK file, it will look where it points to, look for the icon of that, and then map this little arrow for the link on top of that icon. What it does here is it uses a feature where if the link actually goes into special files that are in the control panel, you know, settings and stuff, then it will actually check what the status of this control panel icon is, because those can change. So in order to find this out, it will actually load the corresponding DLL using load library. Now, if you load a DLL using load library, you automatically also execute the DLL's main function, which is exactly what happened here. So you're putting the LNK file and a DLL next to each other, have the LNK file point to the DLL with the status, this is a control panel icon, and then it will actually load the DLL in order to find the icon. That gives you 100% reliable execution of code in the Explorer exit context. The second one, the task scheduler, is essentially it's a CRC 32 compensation attack. So what Windows did, and this is post XP, I think. What Windows does in a task scheduler is when you schedule a task, you can actually set a couple of things like when does it run, under which user context, blah, blah, blah. So when you create that task, it stores an XML file, but the XML file is still owned by the user. Otherwise, you would have a vulnerability right there, right? So when the time comes to execute the task scheduler actually tries to make sure that the file is still the same. So the way they did that was when the task was created, it would actually pull a CRC 32 over the entire file. And then when they execute the task, they would verify that the CRC 32 is still the same. Now, most of you will probably know that CRC 32 is not a cryptographic hash and can be compensated. So what the attack does is it creates a task, the XML gets written, then it changes the user as which the task is to be executed to administrator or system, and then pats the file until the CRC 32 is the same again. And so when task scheduler actually runs the task, it will execute it as a privileged user. Again, this gives you 100% reliable code execution. We don't have a single buffer overflow in here. This is a pure logic block, right? So, Windows XP and lower don't have the task scheduler in this form. They are not writing XML files, so they needed another vulnerability. This one here loads the keyboard layout. So on XP and below, the keyboard layout that you're loading, the layout file, can be anywhere, right? Later on, Microsoft decided it must be below the system directory. Now, on XP and below, it can be wherever you want, and you tell the operating system to load the file. Now, they have an unchecked index within this file. So the file has an index into some table. They're not checking the index. The table actually only has like 4 or 5 entries. What happens if you put a higher index in there, it will go past the table somewhere and then call code. However, this is actually done by the kernel. Now, they needed to find a way to actually reliably execute code, although it's in kernel space and they don't know how the memory in kernel space is going to look like. So what they did was they're actually scanning the memory of the resulting memory of the loaded key map for addresses that are below the magic number of 8000000. Hence, they're in user space. Then they run a program, a wrapper program that maps at this address that they found a memory page with actual code, and then this program causes Windows to load the keyboard layout. Pretty decent and also 100% reliable. Next thing, printer spooler. That one was fun. So usually when you print on a remote print chair on a print spooler, what the print spooler does is it looks up your user credentials and then impersonates the process itself as the user, right? So it's printing with your permissions and not with someone else's. Now, the issue is if you're an anonymous user, like null session, for example, on a Windows system, Microsoft had an issue figuring out, well, who do we impersonate here? So, well, we don't. We're doing it as system. Now, that by itself wasn't really a vulnerability. The interesting part is that when you print, you can also submit a so-called MOF file. Funny side story, the Microsoft security researchers spent about a day finding someone at Microsoft campus who even knew what MOF files are and what they're doing. Well, the attackers did know. So what they're doing is they're essentially like a little bit like PostScript. They're controlling scripts for the printers so you can set up the printer correctly. So like, what page orientation, blah, blah, blah. Also, you can execute commands. You can execute code. So what happens is you're submitting the MOF file together with the print job, and you embed an exe file into the MOF file. It ends up in a directory, in a special directory under this system32, and then Windows continuously scans for the MOF file and fires it off. Just runs it as system. Well, that gives you 100% reliable remote code execution. See a pattern? What's also interesting is the 2008 service vulnerability that they're using. It's a very old RPC path canonicalization bug that apparently still really works really well in some parts of this globe, as we're recently seeing with the Duvu, or however you pronounce that thing. Code reuse, Stuxnet or not thingy. Well, all those compromises apparently come from the same vulnerability. It's a pretty straightforward path canonicalization issue. In contrast to the other vulnerabilities that we already covered, this one actually doesn't have 100% reliability. But seriously, if you look at Metasploit and the list of targets that are within the Metasploit module, and the sheer amount of people that have successfully used this vulnerability to gain access to something because they forgot the password or whatever, there's enough anecdotal knowledge about this vulnerability that you can make it almost 100% reliable. So this plays pretty much in the same room. To get around host-based IDS systems, they have a very, very nice trick. Well, the host-based IDS is snake oil, obviously, but they wanted a general way of doing that. So essentially what they do is they're hooking the load library calls. And when you do a load library call, when they're trying to load their own libraries, Stuxnet is all DLLs and DLL sections, right? When they try to load their own libraries, they're just appending bullshit on it, right? Bullshit, but bullshit in a discoverable pattern. So in a regular case, they would just pass on load library to its original function. In their own case, they will actually correct the file name before loading the library. What the host-based IDS sees is the original file name that they're trying to load with all the garbage. It tries to open the file, gets a file not found error, goes like, whoop, that DLL doesn't exist. I don't need to inspect it. Very easy. This is what I like the most. So apparently they made a pretty good statistic on who uses what antivirus solution within their target area. And so the antivirus vendors always tell you, no, we don't just do signatures, we also do heuristics and we look at the performance of the processes and their behavior. Well, not all the processes. Some processes actually do all the things that viruses do for a legitimate reason. You can probably guess that Alice ASS is one of them. Alice ASS does all the things that usually just viruses and malware do. And it's also pretty hard to monitor, so they're just excluding it from the monitoring list. Or even better, some of the antivirus processes don't monitor themselves. Because, well, I'm the antivirus process, right? I can't do anything wrong. So what Stuxnet does is actually injecting threats into Kaspersky antivirus into its own process and runs within Kaspersky. That's just the neatest way to show the antivirus industry how much snake oil they produce. There must be some real fuck up in eTrust version 5 and 6 because they're actually just bailing out if they find this. Alternatively, they're running it themselves. Then for the project files. So Stuxnet actually goes ahead and patches all the project files for the Step 7 development environment. So Step 7 is the environment that you program Siemens PLCs with. The project files are essentially big zip files with a certain directory structure in it. It's somewhat smart because every Step 7 installation has a bunch of sample files and example projects. It's not infecting those, and it's never infecting projects that haven't been touched for 3 or longer years. So it's not infecting old stuff, it's only infecting somewhat old stuff. Now, Siemens apparently finds it totally acceptable to have the following mechanism within the project loading file. Like the projects are just PLC code and wiring diagrams and stuff. But if it finds a DLL in a certain subdirectory, it will load the DLL for obvious reasons. I don't know. They're not considering this a vulnerability. There hasn't been any fix to it. But this is what Stuxnet actually does to every project it finds on an infected computer. So it's like a regular file infector in the old MS-DOS days. Similar to the Step 7 infection, it also looks for WinCC servers. Those are central database servers that you can use if you manage more than one project. They have a hard-coded username. Username is SA. They have a hard-coded password that is hard-coded in all of Siemens software that cannot be changed. Well known since 2008. Siemens never considered that a problem. So they're using that password and the SA database super user and infect all the projects on the servers as well. In order to actually get onto the PLC, they're infecting the DLL that is performing the communication with the actual PLC devices. Regular function hooking, they take the original DLL, put it to the side, give it a new name, put a new DLL in, hook all the export all the right functions, call them back into the original DLL, except for a couple of them that read and write, and then they modify everything on the fly. So when you write to the PLC, you get Stuxnet PLC code additional to it. When you read, it's extracted from what you read. And there's an additional monitoring thread they introduce to the software that monitors the PLC. So Stuxnet infected PLC is actually better monitored than one that isn't infected, because there are two different monitoring threads now. And there's another thread that they use for controlling. Before they infect the PLC, and this is actually quite interesting, they're trying to fingerprint their target system. And this was thought of to be more complicated. So we learned from this that it's actually a lot easier than we thought. So first of all, they check if the right type of PLC is used, like the PLC CPU types, whether there's a Profibus interface, so if it's networked or not. If it's not networked, not what we're dealing with. And then Profibus actually uses identification numbers. They're very similar to like the first three bytes of your MAC address that usually tells you the vendor of the network card, right? This is the same with the Profibus identification. Profibus identification, vendor assigned numbers, so they can actually check the numbers on the Profibus and see whether they find a Ferraro or a Vacun variable frequency drive and the right number of it. So they need, I think it's like 33 in a cascade, because they're looking for a cascade of centrifuges, right? So they check whether those devices are on the Profibus and nothing else. And only then they're actually infecting the ICS. There's a couple of blocks in there. Symantec started to call them block A, B, and C, so I'm going to stick with that. Here is a comparison between block A and B. You can already see, this is BinDiff, you can already see that they're identical. The only thing that's different between block A and B is actual values they're writing to the variable frequency drives, because block A is for the one type and brand and block B is for the other. So completely redundant. Maybe they didn't know what to expect. As I said, they're redundant. The third block C is still a bit unclear what the purpose is. There's a couple of theories. One is that it's actually targeting another facility, in this case, the Bushehr nuclear power plant. I'm not really in favor of that theory. The block looks like either it's a leftover or it served a certain purpose that it actually never executed. So that's the PLC part, in contrast to all of the other parts of Stuxnet, actually shows a couple of sloppiness in design and construction, but that's probably because it's old. So essentially what it does is, what block A and B do is exactly what Jason described in the video, is they're recording the traffic on the Profibus, the controlling traffic, because they don't really care what the centrifuges actually do at the moment they get infected. They're just recording it for a couple of days. And then use the recordings as a template for the commands they're going to send out. So you could actually change the programming of the control process to use a different protocol. You could change the structures, everything. They don't need to know that. They're just using what you're using on the network. It's almost like blind fuzzing a binary protocol. So they record all the codes and then later on spill it back. They infect two different areas in the PLC. One of them is called the organization block 1. That's the core execution point of every PLC. And the other is the OB35. It's a timed execution. It's like a watchdog, which they use to monitor the healthiness of the PLC and the Stuxnet itself. What was widely published during the first phases of analysis of Stuxnet was a monitoring code that is in OB35 that actually tells you whether the device is infected or not. But this is, but this actually turned out to be not the key functionality within this watchdog. The watchdog was actually more for controlling the health of the whole device installation. So this is what I just mentioned. So they record the frames, and then they wait a couple of hours, and then they actually send a couple of bursts to the different variable frequency drives. What this means is they're not trying to destroy anything. What this means is if you have a uranium enrichment process, you have a very long runtime of the centrifuges, so it goes for days and days, and then you move the uranium into a different cascade of centrifuges, and so on and so on. So with those short bursts of the speed of rotation, they essentially fuck up the process. So the uranium enrichment is no longer enriching. That's all they do. And this is why it was so hard for the Iranians to actually figure this out by themselves, because they just had uranium failing their tests, and they had centrifuges dying on them, and they didn't know why. So the international nuclear oversight, whatever they're called, they have some cameras in the actual facility, and after the whole Stuxnet thing became public, they got all the video footage that they had from the cameras and started counting. And they started counting how many people with centrifuges on their backs actually walked out of the facility the last 2 years, which turned out to be a couple, like almost 2,000. So they actually lost a shitload of centrifuges to that. So talking about the states, here's the actual code that you use to figure out from a infected step 7 to the PLC whether Stuxnet is currently in action or not. So whether you're currently having a burst or not. So I don't know if this is interesting. I'm gonna skip this. This is actual PLC code. So the interesting thing here is one attack cycle goes 67 days. It's very, very unlikely that in a regular operation of any industrial control process you would notice that. If it would happen like every day at noon or at midnight or whatever, that stands out like a sore thumb. But if it takes over 2 months for one attack cycle to happen, then it's very unlikely, even in your management dashboard and the SAP plant monitoring system, you will not see it because it's a very tiny spike over a very long period. Here comes the best hack of all, I think. In the video, we saw that they were using ARP man in the middle in order to spoof the operator. This is actually a big advancement here. So the OB1, the organization block 1 of the PLC, is the piece of code that gets called in cycles, like continuously. And this piece of code calls off everything else. The way PLCs work is, before the organization block 1 is called, all the sensors, all the readings, everything from temperature sensors to whatever you have, is queried, and you build a table of your inputs with the specific values. Once your code ran and read from this input table, it writes to an output table. And then once your OB1 is finished, it takes the output table and sends the signals in the output table to the respective outputs, like your engine control, like your Profibus interface, or a heater, or whatever. Or an automatic dildo, whatever you have connected to your output. Now, what Stuxnet actually does, it uses an undocumented feature of the Siemens PLCs that turns off this automatic updating of the input and output tables. So the moment Stuxnet infects OB1, it will actually change the input before it's seen by the real code. And once the real code wrote to the outputs, it will actually change the outputs and then manually write the tables to the connected equipment. And they need very little code for that. That's all the code they need. It's an undocumented feature, but it's a feature of the PLC, so they can simply call the PLC to do it. This is pretty cool, because now they virtualized the PLC within itself. The PLC doesn't see what is connected to the PLC, but what Stuxnet wants it to see. Here's a trick that I said there's some sloppiness in the PLC code. Here's a trick that many ICS engineers use. You can use hints in the code. There's opcodes called BLD that will hint to the Siemens disassembler what a certain block of code does. And commonly, you can use those opcodes. They're not doing anything on the PLC. They're like knobs on a PLC. But for the disassembler, they give you a hint on what this block of code used to be. So macros that you used to have can be disassembled into macros again and not into the actual code that the macro generated. Stuxnet actually doesn't use the trick of intentionally including evil BLD instructions. So what you can do is, For example, you can say BLD 7 and 8, which shows here to the disassembler, hey, here comes a call instruction. Then you have a condition here that is always true that jumps over here, and then you put all your EVA code in here. And this unconditional call to SFC46 is what the disassembler then is going to show in the disassembly. He's going to only show this one line, which is exactly the reason that I wrote my own disassembler for this whole shit. And it turned out to be useless because the Stuxnet authors didn't use this fucking trick. Assholes. So, what's reusable about this? Well, there's a lot of stuff reusable. We're seeing it with Dooku, or however you fucking call it, now that it's obviously a exploit kit that they used, and now it's getting reused for more mundane purposes, like installing keyloggers and watching other people entering their porn site passwords. But essentially, for a targeted attack, all the spreading mechanisms, all the rootkit driver that they obviously bought from someone else, all this craft wasn't really necessary. My theory actually is that when they had the exploit kit with all the PLC code and everything, they would actually give it to one of the new cyber warriors. You know, the former Air Force people that were too dumb to fly a plane and now are repurposed to be cyber warriors. They probably gave them the entire exploit kit, and then someone went like click, 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 fire. That's probably what happened. And now we're seeing someone more smarter doing less checkboxes. I'm almost done. What you actually need for a targeted attack, the step 7 project file infection. Well, since Siemens doesn't consider it a vulnerability to execute code when you load a project, this is still open for you. You need to fingerprint the ICS. Not a big deal if you know what you're targeting. The backdooring of the step 7 is actually fairly optional. You can actually send the code by yourself. And the virtualization of the PLC is necessary to spoof the operator, but as we have seen, it's very little code. The relevant functionality isn't spreading. And of course, nowadays, after Din's presentation at Black Hat, we all know that you can also just telnet into a Siemens PLC with a fixed password, get a root level shell, and patch the underlying operating system, or see monkeys on a red background. That is also another avenue of attack here, obviously. So the problem with Stuxnet is actually that once you understand how little of it is actually needed for a targeted attack, it becomes a lot more accessible for less talented attackers to actually use that against the competition, especially if your competition is sitting in India, China, or whatever. So, current defenses. Well, Siemens' point of view, even with like root level access to the PLC with fixed username and password, is security is the issue of the customer. They have a senior manager of hack-proof products that is actually, traveling around the world and telling everyone security is the problem of your customers. Why he still has a job is beyond me. As I said, the code execution when project load is not considered a vulnerability. The fixed password on the WinCC server, well, they came around to say it's suboptimal design, but don't imagine that they're putting out fixes. At the maximum, if they're putting out fixes, I would actually check the fix whether it just changes the hard-coded password to another one. Air gaps, you can ask pretty much everyone in our industry. If someone walks up to you and says, well, that never happens to us, the network is air gapped from the internet, he's lying. Because one of these operators probably has a wireless access point so he can surf porn. That's very, very clear, especially if you pay them like $6 an hour. And as I said, the dashboards for management and agile production environments all require for your stuff to be connected. Virus scanners, well, if you still believe in virus scanners, then you can also just believe in Santa Claus protecting your systems. That, you know, they haven't helped us since the 70s. ICS engineers actually have a pretty good idea. They say, well, the code on a PLC is not supposed to change by itself. So how about we just have a separate machine that we're not touching that frequently reprograms our PLCs? That's actually one of the smarter ideas. However, of course, how do they move the code over to that separate machine? It's going to be with a hash days batch, USB in, well, owned. Oh, by the way, did they mention that I put a Stuxnet follow-up on the batch? No? Did you put it in your USB? Yeah. There is Ralph Lindner has a, he kind of played the media czar on Stuxnet PLC side. He actually has a controller integrity checker, which is a standalone program that queries the PLC for a couple of variables and what code is on them. It is one of the better ideas. It is Siemens specific. It doesn't help you if the attacker just used the well-known username and password to telnet into your PLC and root it that way. And of course, it has the detection paradigm, aka AV issue of not seeing shit if the attacker knows that you're using it. But it's one of the better ideas. The actual thing that we need to do is we need to study those environments more. We not rely on the few people like the Idaho National Laboratory to demonstrate how to turn off power. If you have an industrial control system, go look at it yourself. Make actually sure that you know those non-existing air gaps, where they are. How does code actually get into your system? What change control measures do you have in place for your external consultants to put code on your control system? Do you actually have the fucking code that's running your production line? That would be a good question to ask. And the second question, where is it? Can I see it? We actually need to look at them individually and then build a threat model around it. That's right now the only defense we have, because there is nothing boilerplate, nothing like a silver bullet we can take out and shoot at them. And that was it. Only slightly over. Questions? It's in clear text. He actually, which one, the WinCC or the? It's in clear text, and it's in every single Siemens application because they all need to talk to the WinCC. Same also for the, I think the other password on the PLC itself was Basilisk or something. Didn't actually stumble across it because he pulled a memory dump out of it, and it actually said in clear text like password Basilisk. That's the level of shit we're dealing with here. And this is just not just Siemens, like Rockwell Automation and all the other players in the PLC market. They're the same level or worse. This is German engineering, my ass. But imagine Americans doing the same thing at Rockwell. It's not going to be any better. Just bigger. Any other question? One last thing I wanted to mention is I said that the PLC code in Stuxnet is kind of sloppy because it's probably so old. Just for your reference, the code was compiled, and they actually left the compile timestamps in there. The code was compiled in September 2007. So the attackers actually completed the PLC part of the attack code in 2007. Anything else?